So, hi, great to see you all. So, let me start by trying to motivate why we need to automate driving in two numbers. So we actually already seen these numbers in previous talks. So the first one is the number of traffic fatalities each year globally. So huge number. So this is the leading cause of death for children and young adults in this age range. And we have, on top of this, about 50 million injuries, traffic-related injuries yearly, sometimes resulting in lifelong disabilities. So I think it's clear that this is a huge societal problem, and we need to do something about it. And one possible hint on what we could potentially do about it comes from the fact that about 94% of these traffic crashes are caused by the human error that we also heard about previously. So that tells us that there's an opportunity here, that we could save a lot of lives by eliminating the human errors and automate driving. And the thing about driving collision is that no one expects them. Everybody thinks they're a great driver and that it wouldn't happen to them, but then all of a sudden, there's a car that has crashed and is standing in your lane. So I will say first a few words about my company, and then I'll speak a bit about different software stack approaches, sort of software designs for autonomous driving that exist today. And then I'll say a few words about some different research projects that I've been involved in, and then we'll talk a little bit more about a new dataset that we are releasing, the Zenseact open dataset. So our vision at Zenseact is a world with 0 road traffic fatalities and 0 injuries. And our motto is towards 0 faster. And we want to realize this vision by developing world-leading autonomous driving and advanced driver assistance system software for consumer vehicles. Our lead customers are Volvo Cars and Polestar. We are located over at Lindholmen, and we have a smaller office in Shanghai. So we're a bit more than 500 people with a bit more than 60 deep learning engineers currently, but this is expected to grow. So what is this sort of software challenge that we are facing for autonomous driving? And you can frame it as this, that we have a very capable set of sensors. We have high-resolution cameras. We have radars all around the vehicles. We have a LiDAR. We have maps. So the question is really how to design and develop the software stack that performs this map from this really, really rich sensor input data stream onto driving, onto steering and acceleration. So one sort of traditional way of thinking about this is to sort of divide this very complex task into more chewable subtasks, which are a bit simpler. So for example, you can have that the camera, you can have a camera image coming in to the first block. So for each image frame, you would detect all the objects and the lane markings and the traffic signs and these things in a frame-by-frame manner. Then you would send all those detection for each frame to your tracker that would do the temporal fusion. And based on that, you can then sort of estimate the velocities and the directions that the other road users are going. And then based on that, you can make some predictions of where they are likely to end up in the next few seconds. And then based on that, you can do your own ego trajectory planning, the planning for your own vehicle. And then you would perform control with respect to that ego trajectory. And then the final output would be your steering and acceleration commands. So this is the sort of traditional approach. And 10 years ago, no one was using deep networks, of course, but these days, everyone is using them, at least in this frame-by-frame detection blocks. And just to give you some examples of how such networks can look. So here is a vision-based 3D object detector. So a network where you have the input is just a single frame. Here we're just showing it in a sequence, but only a single frame is in the input. And then the outputs are these 3D bounding boxes. So the physical location and size and orientation of the different objects. And similarly, you would do frame-by-frame detections of lane markings, the road edges, the barriers, drivable free space, traffic signs, you name it. All these kinds of useful information that you want to extract from your sensor data. And so there's some pros to this sort of very modular approach. First, you have this very simple human interpretable interfaces between the different blocks. That's great. That's easy to understand. But the problem is that these interfaces may introduce really severe information bottlenecks in your software stack. And so you can imagine that you have this really, really rich, multi-million dimensional sensor data inputs coming into this block. But in this block, you're sort of completely compressing all that information to just like a small list of these featureless bounding boxes, for example, or points for your lane markings. So all that information is almost gone through the rest of the stack, right? And that could potentially be a huge problem because there could be information and cues in the sensor data that will turn out to be crucial for making really robust predictions or planning, for example. So if we take the example of how to make really accurate predictions, well, it could be that the system needs to pick up on several subtle cues, like all the past behavior of the other road users, their motion, if the turn indicators is active, the brake lights, the distances to lane markings, and if that is changing, the sort of lane and road geometry and topology. If the driver is turning his or her head to check the blind spot, that could be a clear indication that that driver is about to merge into your lane, even if the turn indicator is not on. And so on and so forth. For pedestrians, you would have the pose, the motion, the face direction, the gestures, and so on and so forth. And the traditional approach would be that this modular approach, that you would design dedicated algorithms for at least a subset of all these cues. And this can be done, for example, by these frame-by-frame networks. But then you would combine all these different outputs for all these different cues with some rule-based logic. Whereas the more end-to-end approach that we will advocate for is to instead train a network on sequence data. It has to be sequence data because the network must be allowed to pick up on these temporal cues that are related to motion and intentions and behaviors of the other road users. And then you would just optimize that network directly for that end task, that prediction task, so that the recognition and the combination of all these cues would be done implicitly inside the network. So if we're advocating for end-to-end approaches, why not just take it all the way? Just have one big network where you feed in sensor sequence data and you output the steering and acceleration commands. From a deep learning perspective, this would be great. That would be an incredibly simple stack. You would also get annotations for free because you can just log the driver's steering and acceleration commands and you train on that. And also, since you would be optimizing directly for the actual driving task, you would expect to make fast progress on your driving capabilities, at least in the standard scenarios. But the cons are, of course, this lack of interpretability. That if the system makes an error, then it's really difficult to understand what was the source of that failure mode, how to fix it, how to collect data that is needed, and so on and so forth. And also, unless you have a really good and robust way of estimating the uncertainties of the network and the network outputs, and you're just driving blindly on the outputs of the network, then of course you have the usual problem that you have in machine learning, that if it turns out that you have an input data sample that is way out of your training distribution, then God knows what's going to come out of it. So then it will be very difficult to achieve and verify safety and, for example, traffic rule compliance. So why not take the best of both worlds? So to have a network where you would feed in sequence data from all your sensors in order to pick up those temporal cues. But that you would, so you would do both the temporal fusion and the sensor fusion inside the network. And you would directly optimize towards these more downstream tasks, like predictions and even proposing ego motion trajectories. You can also have some additional outputs, mainly for debugging reasons, and also if you have the annotations for extra supervision signals. So for example, like for lane detection and object detection, and also object tracks, for example. Also to understand sort of what went wrong if in the system. It was because the predictions were wrong, or the tracking was wrong, or the detections were wrong. But then you again have this benefit of having free annotations for your ego trajectory proposal. Again, just by logging how the driver actually, which trajectory the driver actually took. So you can train on that. But you would, at the same time, these proposals that is outputted by the network, you could still evaluate them and validate them in a planning block. So you could still check that they are safe. So you would put some, like many checks and safety guardrails around your deep learning system, basically. But that still means, so in this sense, you can achieve and verify safety and traffic rule compliance. But it still means that if those ego trajectory proposals made by the network turn out to be of sufficient quality so that they would actually pass all those safety checks and they would actually be within the safety guardrails of the system, then those could be the trajectories that we actually drive on, that we actually send to control. And that would mean that we would really be driving completely in a trainable end-to-end fashion. We're not really advocating for using deep learning in the control part, because it's not obvious that it would help. Because once you have that ego trajectory, then the remaining task is sort of low-dimensional, vehicle-specific, and typically quite well solved with traditional control methods. But of course, this will require a very large and diverse set of data sequences. So that means that we will need a whole fleet of consumer vehicles that are collecting data. Luckily, we will have one with the next generation Volvos and Polestars. And also, what's probably the bulk of the work is to really develop an extremely efficient data pipeline for generating the training data, for turning those raw sequence data into training data with supervision signals. Because we want to use that in order to fuel this stack and allow this kind of learning-based stack to expand in terms of the operational design domains, to generalize to new roads, countries, weather conditions, and so on as absolutely fast as possible. Okay, so let's switch gears a little bit and talk about some recent research projects. So the first question is, what on earth could Zenseact and CERN have in common? So CERN is this particle physics laboratory outside of Geneva in Switzerland. So it's clear that they have very different goals than Zenseact. So we want to push traffic safety to the next level. They want to push human knowledge about the fundamental building blocks of nature to the next level. But it turns out that we both have this urgent need for really accurate and really fast deep learning algorithms. So at Zenseact, we need them to process all that sensor information that is continuously streaming, and that processing has to be done in real time on device in the car. And at CERN, they are colliding particles 40 million times per second, generating enormous amounts of data. So they need deep learning algorithms to go through all those events online really, really fast and filter out the bulk of those collisions that they're not interested in. So what we did is that we developed an automatic pipeline for reducing the bit precision of the weights in the network, so-called quantization-aware training. Also to remove the least important weights in the networks. And then once you're done with the compression during the training, We did this fully on-chip deployment on hardware, configurable hardware called FPGAs. And we showed that for some computer vision networks, we could actually remove half of the weights, reduced the bit precision of those weights down all the way to 4-bit integer representations, which is a bit further than what is typically standard as deep learning inference, which is int8. And we saw that this led to a reduction of latency, memory usage, and power consumption on the chips. And all this without significantly reducing accuracy. That was great. Next question. Can these networks sort of learn anything useful for autonomous driving without manual annotations? And I think it's clear from many talks today that by now the answer is clearly yes. We have self-supervised learning. Probably the most famous example is the language models and the GPT series where you predict the next word or the next token. But of course that next word is already in your data, so you don't need any sort of manual additional annotations. So something similar has already been shown works well for transformers in computer vision. So you just patch up images, you mask out some patches, and you ask the network to reconstruct those patches. Of course, we can do the same thing for our automotive images. What we did in this paper was to do the analogous thing for point clouds. So we proposed this method for self-supervised pre-training on voxel representations of automotive point clouds. And we did this self-supervised pre-training on backbones of different transformer-based object detectors on LiDAR point clouds. And we showed that with such self-supervised pre-training, the model only required 40% of the annotations for the final end task, so the 3D object detection task, compared to the same model that was not pre-trained. So in addition to being super efficient in terms of reducing the need for manual annotations, we also have the benefits that because these networks are now pre-trained on these proxy tasks. So these tasks is not related to the end task. There are some, so they learn really general representations of the sensor data, which means that you can take the same self-supervised pre-trained network and use it for many downstream target tasks. This also provides a really nice utilization of all your unlabeled data, which is typically orders of magnitude more than your labeled dataset. And we're also seeing that you can use it for really efficient adaptation to new feature domains. Next question. Can you talk to point clouds? Of course you can. So what we did in this paper, which was really driven by Georg and Adam, we started from CLIP. So this model trained on like 400 million text image pairs from internet, where they embedded the text and the images, and then you train them against each other contrastively in order to learn this joint embedding space with really rich representational power. And we would like to do something similar, but instead of images, we would like to connect text and point clouds. But we don't really have any huge data set where you have this text point cloud pairs. But we do have huge automotive data set where you have image and point cloud pairs. So what we did is that we took the CLIP image encoder, and we used that to embed our automotive images. We froze the weights of that network, and instead we use it to supervise the embeddings of the LiDAR point clouds in our dataset. So in this set, we were able to map all our point clouds in our dataset onto that joint embedding space of CLIP. And once you've done that, you can do all kind of fun stuff. You can use it for like data mining and like corner case curation. So say that you would like to find point clouds where you have a dog on the road. You embed that sentence to the clip space, you embed the point cloud, and then you do a similarity ranking, and you can retrieve the point cloud that is mostly resembling the input text. And if you want, you can also include the image, the associated image in this, and I will give an example of that in a minute. Other fun stuff to do is you can also embed the point cloud, and you can do zero-shot classification. So you can just take a set of sentences like a blank on the road, and you can replace blank by car or pedestrian cyclist. So that becomes your 3 different embedding vectors, and then you can do a similarity matching with the embedded vector from the point cloud, and in this way you can classify what is most likely to be in the point cloud. Or you can do sort of LiDAR to text generations. You do captioning generation, generate some text that sort of describes what's in the point cloud. Or you can just run a stable diffusion model to generate an image based on that LiDAR point cloud embedded vector. So here's one example of, just to show that it can be extremely useful for finding really safety critical training samples. So say that you want to find images that are like corrupted. They are blurry, or there's a lot of glare, or water spray on the camera lens or something like this. And you also want there to be nearby pedestrians. Okay. And so if you ask only the images, then you will typically find either or. So if there's a lot of corruption, you typically won't find the pedestrians, and vice versa. And of course, the LiDAR doesn't know anything about corrupted images. But if you instead sort of separate the prompt, so you ask the images to give you an image that is corrupted, and you ask the point cloud to give you point clouds where you have a nearby pedestrian, which makes sense because you have this range knowledge in the LiDAR. And then you do a joint retrieval. So you combine the similarity scores, and that gives you a point cloud image pair for which the image actually contains a corrupted image where you have nearby pedestrians, which is so a super useful safety critical training sample. Okay, so to the open dataset. So we are releasing this now, and you can access it via this web page. And yeah, it's about 100,000 fully annotated images and point clouds, with also some extra sensor data around these individual frames. And then you also have a 1,500 20-second sequences of full sensor data. So in addition to being one of the largest AD datasets to date, there are also some unique features that we actually have the highest diversity in terms of number of countries, weather conditions, and so on. The highest resolution sensors, 8-megapixel camera, super dense LiDAR point clouds, really long range annotations, objects up to over 200 meters, which is of course critical for highway driving. And it turned out that it actually is the largest data set in terms of traffic science. And we provide 2 different anonymization methods. One is the standard blurring, and the other one is more like generative or deep fake, sort of replacing faces and license plates for synthetic ones. And it's also under a very permissive license. So in addition to all kinds of open research, you can also use it for commercially. So even startups and commercial entities can use it for their projects. So here's a sort of a heat map over the geographic diversity where we collected the data over 2 years from 14 different European countries, all the way from snowy north of Sweden to sunny Italy. And if you calculate, depending a little bit how you calculate, but when you calculate the geographic coverage, you will see that our data set is actually between 10 and 30 times bigger than the other sort of leading AD data sets on the market. So we have urban scenes, we have nighttime scenes, we have rainy scenes, we have snowy scenes. So quite different from the usual AD datasets, which is typically from like sunny California. We have lane marking annotations, the Ego road, 2D and 3D bounding boxes for static objects, for dynamic objects, and also these 3D bounding boxes in the point clouds. And it's just an example of some of the different traffic signs, and you will see a bit of this diversity. And here we see the data collection car driving through a scene, and here's the point cloud. You can see the level of detail and the density of the point cloud, and here it's the LiDAR points are colored in the corresponding to the RGB values of the camera. Okay, so that's the great team behind the data set. With a mix of PhD students, researchers, and developers at Zenseact. And yeah, here's some other recent research that I've been involved in. If you're interested, just come and talk to me. It ranges from equivariance to uncertainty estimations to spatiotemporal transformers, motion predictions, and the fact that if you want to do deep learning-based computer vision, there's no need to do like traditional handcrafted image signal processing. It's better to just train on the rawest possible format of your images. Okay, let me just conclude. Our goal is to eliminate traffic fatalities and injuries. But of course, developing autonomous driving software that is truly safe in all situations is very challenging, and we believe that in order to be able to do this, we must really maximally leverage data and learning and AI. So if you're interested in joining us in this, what is sometimes called the space race of our generation, check out our career site. We have a bunch of openings for all levels. Thanks a lot.
Thank you very much, Christoffer. We have very limited time for questions right now, but you promised that you might be around, maybe
absolutely.
in the networking area, which is the allocated tables just outside these halls. And maybe if you have questions and you didn't have time to ask, please go there, because Christoffer will be there. But I get to ask you the first question. So, well, first of all, thank you so much for any open data set that you can provide. I think we need more open data sets.
And I hope that as many people as possible will work on it.
I don't know how you managed to get a license which is even open for commercial use, and we will talk about that one day. But before we start with the audience, I really wanted to ask you, as an Italian citizen who for some mysterious reasons has been entitled to drive, when are we finally going to have self-driving cars?
Yeah, that's the tough question. They already exist, right? There are robotaxi companies that are already operational in San Francisco and Phoenix and some other places. So that's a completely different kind of industry that we are not in, so the robotaxi industry. I think they have some problems of their own, sort of finding the business model and making sure that they are not sort of slower and more expensive than Uber, and but that's something different. For consumer vehicles, I don't know. It will. I think by now it's clear that it will start on limited scales. You would start with a problem that is not the full operational design domain. For example, our plan is to start with highways, because we believe that could bring value, and it's also a domain where it's a bit simpler in some aspects, because you don't have all the pedestrians and cyclists and really complicated interactive scenes. But you do have other complications, which are the high speeds and the need for really long-range sensing and perception capabilities. But exactly when and how. So one question is when, of course, but then the key question is how fast can you scale once you have something that is starting. And our approach is that we start with something limited, but we have cars out everywhere that have the full set of sensors that are collecting data that we can use in order to improve the algorithms. And in this way, we hope that we can scale really fast and expand the operational design domain, that we can bring safety to more roads, to more countries, and yeah.
Fingers crossed.
Yeah.
Maybe we have time. We have time for maybe one quick question. Yes, and we really have just 1 minute. Well, -1,
Sure.
but
Okay. You said that you add this planning block when the output of this big black box doesn't have an uncertainty on the output. Can you estimate an uncertainty to it? And is that something you do as well as in other models?
Yeah, absolutely. So this is critical. I think there will be a combination. There will certainly be uncertainty being estimated by the network itself, which is sometimes called this aleatoric uncertainty that has to do really with the noise level of the data, sort of the intrinsic difficulty of the data sample. There will also be also need to be methods to sort of estimate what is called the epistemic uncertainty, sort of the out of distributionness of the input data sample, sort of how far away from your training data feature domain, yeah, all the feature distributions of your training data. And then on top of that, there could be additional expert networks or handcraft or traditional algorithms that are checking all these. I think it will in the end be quite a complex system, but understanding the uncertainties will be absolutely critical. But it's also important to understand that one of the key reasons why you want to have a pretty big network that does the temporal fusion and that brings information all the way from the sensor all the way to your downstream task is really to bring along information about those uncertainties, because they typically exist in that sensor data. We understand them as human, but if we compress that information too soon and we don't propagate it through the stack, then we are sort of losing a lot of not only performance, but also information about the uncertainties that were actually present in the sensor data, but that we don't have access to in the downstream tasks.
I'm afraid we don't have any more time for questions, at least here in this room. Thank you so much, Christoffer. Thank you for being our speaker.
Thank you very much.